been long since I had the class with students in. Yeah. Anyone who is able to define electrochemistry for us before I say anything? What's electrochemistry? So please just go on. Don't have to raise your hand. Just admit yourself and just tell us, and then.
It is the component of chemistry that studies the change between chemical energy and electrical energy.
Wow, that sounds so advanced. Okay. Anybody else?
It's the study of the interchange between chemical and electric energy.
Okay. I think that's enough, right? We can move on. Um, so in my videos, if you've noticed, um, I want by all means to simplify the idea. So, what is electrochemistry? All the answers that you've given me are okay. So, electrochemistry, which I feel no one will ever ask you to define it, um, just this. Um, Taking that to be chemical energy and then adding the other part to be electrical energy. So we're hearing the terms like interconversions, conversion. So the branch of chemistry that deals with a study of the conversion from chemical energy to electrical energy and vice versa is what we are calling electrochemistry. So there are different cells that we're going to deal with under this topic. So the one that converts chemical energy to electrical energy is called what? N1? What do we call the cell that converts chemical energy to electrical energy?
Galvanic cell.
Okay, so galvanic cell is one that converts chemical energy to electrical energy. So this is the common cell actually that you've seen in the papers that they like assessing you on. Okay, so that's just like a basic diagram of a galvanic cell. Then the other cell that converts electrical energy to chemical energy is called what?
Electrolytic cell.
Okay, so an electrolytic cell does the opposite. Okay, so let's move away from that. That's so simple and basic. Anything else that I can mention? So, of course, we'll later on talk about batteries. I also have to remind you of the importance of balancing, redox reactions, chemical equations, because those are also necessary and important under the study of this topic. So, let's basically just move on by looking at this very thing, a galvanic cell. So we've said the galvanic cell basically converts what?
Chemical energy to electric energy.
So converts chemical energy to electrical energy. Let me try just to draw a quick diagram so that I can just show you the basic calculations that we can perform under a galvanic cell. Now it's very essential for, even as I'm drawing this, it's very essential that under the study of electrochemistry, you need to understand what redox reactions are. So what are redox reactions? So a redox reaction is a reaction where we expect to have what?
Both reduction and oxidation.
So the first three letters there denote reduction, and then the last two represent oxidation. These are the things that you already understand. Some of you are just able to remember. You don't understand them. So there's nothing that is hard so far that we've talked about. So I want you to move with me step by step. I'm trying to be slow to make sure that everyone is at the same page. So we are saying a redox reaction involves both oxidation and reduction. Now, what are these? What is oxidation? So oxidation is so you can use oil and lead to help you remember. So in terms of electrons, oxidation is defined as so oil stands for oil. Oil stands for oxidation is loss, and then the other one, reduction is gain. Are we together? I hope we're on the same page, ladies and gentlemen. So if I give you an example to say we have copper 2 plus, and then copper gets to gain 2 electrons. So what do you expect to have there? I hope you now understand what happens to the charges, right? So adding 2 electrons to a 2 plus, it will just become 0. Now, how is that? Okay, of course, before I explain the charges, first of all, I want you to understand that whenever electrons are appearing on the reactant side, it shows that electrons are being gained. And we call that what? What do we call that?
Reduction.
A reduction. Thank you. So the opposite is true. This very reaction, or this very equation that we have, I can decide to reverse it, where I start with copper, and then on the other side I show that it becomes copper 2 plus, emitting 2 electrons. This very reaction is what? It has now become
Oxidation.
oxidation. So when the electrons are appearing on the right hand side, it shows that they are being lost. Okay. So now with what we have right now, I've already told you to say the second equation that you're able to see is oxidation. So if that is oxidation, what are we saying? So in other ways, if you want to tell, if you have been given a chemical equation to say this reactant or this metal element has been oxidized, you can actually observe by looking at the charge. So if you check, whenever you've got any element in its natural state or with no charge indicated, it shows that the charge is 0. So therefore, in the second reaction, you're able to observe that the charge of copper has increased from 0 to 2. So an increase in oxidation number is also what we call oxidation. Okay? So in case you get confused with electrons, just think about it. Try to observe the changes in terms of the oxidation number. Of course, the other one, you'll be able to see that there was reduction in what? In the oxidation number. So terms actually even make more sense if you think about it in that way. Okay, so I now feel you've understood what oxidation and reduction is without any challenges. Right. Can we move? Okay. So the basic diagram, I'm sure some of you have already even become conversant with the diagram of a galvanic cell. So we need to have the solution, and then so these ones. Anyway, let me add the sort bridge so that we don't forget about it. Okay, so at this point we can now name what we have. So this one is called the sort bridge. Sort bridge. Then these are So that's a metal. It's called an electrode. So even on the other side, there's an electrode as well. Then that's just a wire, where in some experiments or diagrams you find that they even put a bulb there. Okay, to show you that indeed there's conversion from of chemical energy to electrical, because only electrical energy is able to make the bulb go on. So what is coming from the solutions there, from the elements that are reacting, that's where we have chemical energy. Okay, so that's the basic structure of a galvanic cell. We've got a wire, we've got the salt bridge. Sometimes you have what we call a polaris disk. So a polaris disk is a case where you've got that kind of a connection between the two sides. Okay, so that's a polaris disk. So you can either have a polaris disk or you can have the salt bridge to balance the ions there. Okay, so you understand why the salt bridge is there. For now, let's just try to move. So if you've got a question, please ask.
Okay, so my question is, what's the function of the sort bridge?
Yeah, I've said I'm going to explain that just very soon.
That's the first one.
Okay, so we've already talked about the fact that we need a redox reaction, right? We've defined what oxidation and reduction is. So let's assume to say our left hand side is the anode, and then our right hand side is the cathode there. So what would you say? Where do you expect oxidation to occur, and where do you expect reduction to occur? Anyone?
I think
So,
since electrons are moving from the anode to the cathode will gain electrons, and the gain of electrons is reduction.
The cathode would what? Sorry, can you just repeat what you said? Okay, anyone who's able to repeat what she said or anything different?
so I think what you're saying is electrons in a galvanic cell move from the negative electrode to the positive electrode, and then in this case the negative electrode is the anode. Then at the anode oxidation takes place, then at the cathode that's where reduction takes place.
Okay, thank you. So we have movement of electrons from the anode to the cathode. So with that simple explanation, that tells us so that oxidation occurs at the anode, and then reduction occurs where? At the cathode. So let's try to have an example now. This example is going to involve a lot of things at the same time, so just make sure you pay particular attention. So let's consider copper and zinc. So copper 2 plus 2 electrons, giving us what do we expect? It will be copper. I gave you this example already in solid state. And then we can also have zinc. So now if I ask you a question, the way I've written the two equations, are you able to tell which one is oxidation, and which one is reduction? Or they are all written in one way?
You can tell.
You can tell because you're trying to apply external knowledge from what we've not talked about. So, as in the way I've written the equations, what are they showing you? Which one
You can
shows?
still add the negative symbol after the zinc equation. You can just say the zinc in that equation is actually at the cathode, of which is being basically reduced.
Okay, 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 okay. What if they were both negative?
From there, guess what?
Okay, okay, okay. Yeah, so I don't want you to use the negative because sometimes they may all be positive. Yeah. Anyone who is about to answer that question before I actually respond?
For me, I can say we can't tell to say this one is a reduction or is an oxidation because all are written in the same form, and that is the reduction form. Yeah, since the electrons are on the reactant part.
Okay. All right. So, thank you, sir. Looking at the two equations, they are all written in form of reduction. So, that's why I said this example is going to like explain everything about the galvanic cell. So, the way they give you these values, even in your exam or your test, they are all going to be given. Kindly mute your mic. So, we call them reduction potentials because they are all written in the reduction what form. So, these values that you are seeing here are representing the reduction potentials of copper and zinc respectively, and they are all reductions. Now, given the fact that they are being used in a galvanic cell, I want you to take note to say a galvanic cell, that's where we expect a spontaneous reaction to occur. Now, what is a spontaneous reaction? So, a spontaneous reaction is where we don't expect to use any energy or electricity to move electrons. Electrons will just move naturally. Okay? So, we don't need to use any external source or power to make the movement of electrons. It will just be spontaneous. Now, for it to be spontaneous, the E cell is supposed to be what? It's supposed to be positive. Electrons can only move if a standard cell potential, which of course some of you, if you understand the word voltage, it will make more sense. So the E cell, you can think about it as the voltage of the cell. So we need to have a positive value for us to have a galvanic cell where we expect a spontaneous reaction. So in this case, we need to reverse one of these, and the moment you reverse a reaction, the sign of the reduction potential changes. Okay, so think of it in this way. Kindly mute your mic. So if I reverse copper, the reduction potential will become negative. So the question is, if we add the two, are we going to get a positive answer?
No, we get a negative answer.
So we'll get a negative answer. Okay, okay. So you get a negative answer. What if I decide to reverse zinc?
We get a positive answer.
Okay, good. So therefore, I would have to show it explicitly that that's what has happened. So we'll start with zinc solid. So I'm now starting with what is on the right hand side, giving me what is on the left. So the value becomes positive. So as I'm saying, I'm trying to explain all the concepts of the galvanic cell using this very example. So after reversing, the sign has changed. Now what I want you to understand is this. Assuming we had a case where we had, let's say, 4 electrons on the copper part, right? If I'm trying to balance it, before I get to show them, I would have to balance the number of electrons. Now, even if I decide to balance by multiplying the second equation by 2, so that the electrons become 4 in this other reaction as well, never should you change the value of the reduction potential. So we call that an intrinsic property. You understand later on as you look at equilibrium. So whether you multiply the entire equation by a 4, that value there remains as it is. No effect. Okay, we'll understand that later. So if they want you to find the E cell or the cell potential, just add the two values that you have, 0.34 plus 0.76. What are we getting there? Should be something like that. Any questions on how to find the E cell potential? Any question? Are we on the same page? Kindly respond so that we move, if you're able to get me.
Yes, yes, sir.
Okay, so let's assume we are, this is what we had. We had copper and zinc. So I've already reversed the one that what we're supposed to reverse. So how basically can we show, or which one do we expect to be on the anode? Is it zinc or copper?
So I think it's copper.
Copper will be the anode.
Yes, since it's reduction.
So we said reduction occurs on the anode.
Zinc will be on the
Sorry,
anode.
that's
Okay, thank you. So we expect that we have zinc there, solid. Okay. So the other thing that you need to understand is on the electrodes, I said they are metals, right? So on the electrodes that we expect to have a metal. So on the other side as well, you have copper as a metal. Are we together? I want you to pay. So on the electrodes, put metals there. Of course, later on we'll look at examples where you've got like gases as your reactants. In such a case, we use non-reactive metals like platinum to represent the electrode. Okay. So I'm saying in a case where in your equation you don't have a metal, you can use non-reactive metals like platinum to represent your electrode. Okay. And we'll understand all that as we look at next time. I'll teach you how to write the shorthand notation, the cell notation, and all that. We'll look at all those examples, but just take note of that. So what do we expect to have in the solution now? So in the solutions that's where we're going to have the what? The ions, right? So what are we going to have where we've got copper?
we'll have
We have what?
Copper 2 plus.
We have copper 2 plus. Then where we have zinc? Zinc 2 plus. So now let me ask you a question. So what is happening there? What is happening? So where we have copper, look at this equation. So the equation tells us to say what we're having being produced is what? Copper 2 plus is gaining what? Electrons to become what?
to become copper metal.
To become copper metal. Then zinc metal is gaining electrons by the wire. So I'm trying to help you understand the process, what's happening, what's there in action. So the electrons are moving from let me now not confuse you. So the electrons are basically reacting with copper 2 plus, meaning that they are moving from the anode heading to what? To the cathode. So as they get to come in this solution, they are reacting with these copper 2 pluses that are there to form what? The solid metal. Now, where they are leaving there, are you people trying to get what I'm saying here? So where they are leaving, from the side where they're coming from, they are producing zinc 2 plus because the metal keeps on what? Keeps on losing. So after a metal loses, it falls into the solution and forms zinc 2 plus ions. So after some time, if you are to even put a bulb there on this wire, after some time, the bulb is going to go what? Off. Anyone who is able to give a reason why the bulb will go off?
Maybe it's because the electrons would have moved to copper.
The electrons that move to copper. So there will be no more electrons to what? To move from the anode. Okay, that's a good way of looking at it. So what then should we do to prevent that from happening?
Add a salt bridge.
Okay, so we should have a salt bridge. So a possible salt bridge we can have here is can have sodium 2 sulfate. So of course, if you look at that salt, the one that is, if you break it down into its ions, you are going to have sodium, and then you're also going to have SO4. So where do we expect? Let me put actually 2 there to demonstrate that there will be 2 actually. So where do we expect the sodium to go? Anode to the cathode. Remember, it's positive.
I think it will go to the cathode.
It will go to the cathode. Why do you think it's going to go to the cathode?
Because sodium is positive and the cathode is negative, so they will attract.
Okay, good. So the sodium will basically go where there's copper. Remember, where there's copper, there's production of copper what? Copper solid, right? So the sodium is going to go there to react with what? So sodium plus, which is coming of course with 2 ions, will react. On the cathode we said there are electrons that are being what? That are being gained there. So what we are saying is there is overproduction of the solid metal. So to ensure that the electrons will continue moving, on the other side, zinc, which is becoming zinc ions there, is going to react with a sulfate so that it goes back to what? In other terms, not maybe thinking of it as a reaction, we can think of it as in this way. We have zinc 2 plus being produced in the solution, right? On the anode, right? Because that's where we have oxidation. So the sulfate there, a 2 minus in chemistry indicates that it's having two electrons there, two excess electrons. So those two electrons are going to do what? They are going to be reacting with what? With a zinc 2 plus to reverse it back to what? So the zinc will be going back to the metal form, and then the copper 2 plus, is it a copper 2 plus? The copper solid will be reacting with it will be losing two electrons, so that we can also have part of it being in the solution. I think that's the way we can think about it, just to avoid a lot of confusion for now. So the idea of a salt bridge is to balance the ions on the left and the right hand side to ensure continuous flow of what? Of electrons. So later on, again, you realize that if this is what is happening, you end up having again for example, on the right hand side, the whole metal again will become copper 2 plus. So the sodium sulfate and the sodium will now be going like, there's no specific direction where they are supposed to go. They'll be going almost everywhere to balance up things on both the left and the right hand side. What I've demonstrated only happens at start. Okay, so that's the main idea. They will never ask you to show all that. I was just trying to help you get the idea of the importance of the salt bridge.
So just there,
Yes.
how do you know that the sodium are acting with the copper and the sulfate with the zinc?
And how do you know that what?
That the sodium will react with the copper and the sulfate will react with the zinc.
This one, what I have understood from what he's explaining is, let me say, he said from the cathode, we only have, from the cathode, he said reduction takes place. So he says the copper ions will gain electrons to make copper, the metal. So what happens is, so the sodium will go where there is copper, because sodium are positive, and then the cathode is negative. That's why there will be an attraction. The sodium can't go to the anode, because positive and positive, nothing happens. So there will be no movement. There will be no movement of electrons, which means you won't have electricity that you want to get. But then the sulfate, since it's negative, it will go to the anode, because the anode is positive. Positive and negative, there will be an attraction and will produce the electricity that we want. I don't know if I'm correct. You'll correct me.
Okay, that's a good explanation. So using one side, so what we said is on the anode, that's where oxidation is what? That's where oxidation occurs. So if you've got your zinc solid there on the electrode, what will be happening is, as your electrons are moving towards the cathode, even according to the equation there, we are saying that zinc 2 plus ions will be produced where? In the solution, right? So eventually, we can think of it as though the solid metal will be done there, but it will not actually be done. But what we're trying to say is there will be no more metals to lose electrons, because they've all lost, right? So what is going to be happening is, since the anode, we are having positive ions, these positive ions now are the ones that are going to react with the negative sodium ions. So that reaction actually involves this negative ion losing the two electrons, so that the two electrons can actually be gained by the zinc 2 plus ions to give us back what? The metal form of zinc, to ensure that it continues losing continuously like that. So on the other side as well, the opposite is true. Since copper is the one that is being produced, so we ensure that copper keeps gaining, not gaining, keeps losing electrons to the sodium. Why? So that we can continuously have the copper 2 plus gaining the electrons coming from the other side. I think it's more like a cycle. You can think about it in that way. Okay, can we move on now?
And sir, I have two questions. So Josephine is saying reduction takes place at the cathode, and that the cathode is negatively charged. Isn't it positively charged? Then the second question is, what characteristics should a sword bridge have so that the flow of electrons does not stop?
Okay. So the first question is the cathode negatively charged or positively charged?
Yes, sir.
Okay. So according to you, what are you saying?
The cathode. Oh, sorry.
The cathode, is it positive or negative?
I think I read somewhere the cathode in a galvanic cell is positively charged.
You know what?
Galvanic cell, sir.
Uh-huh. Yeah, so that's the way it is. So the cathode and the anode actually values when you're comparing two different kinds of cells. So think of it in terms of a galvanic cell. Is a cathode positive or negative in a galvanic cell? It's positive, right? The cathode is positive when you're talking about it in terms of a galvanic cell. But if you're talking about it in terms of an electrolytic, what can I say? Yeah, electrolytic cell, you expect it to be negative. Okay, but that's not even important anyway. I don't know why. Yeah, it's not important, but that's the case. So under this case, the cathode is positive.
Okay, sir.
Then your second question is that what are the characteristics of a sword bridge to ensure that there's continuous flow of electrons.
Yes, sir.
So I'm sure you've noticed something about how I wish I could say that you know of course what a sword is, right? So there's actually the good part is there's no restriction actually on the sword bridge, because if you look at magnesium, right? Let's say we had magnesium sulfate as our salt. The only difference there would be in terms of that salt, magnesium would need not to have what? The coefficient of a 2. Why? Because it's already having 2 plus. Are we together?
Yes, sir.
So how I wish I would have mentioned something like that, but I'll give you the actual points where on what are some of the characteristics of a good sword bridge. Of course, one thing that you can think about is there should be at least that desire for or that affinity between the negative ion and the positive ions. Okay. So any question on the galvanic cell? Any question on the galvanic cell? So I need to mention that the E cell, where we wrote something like this one is called standard cell potential. That is only the cell potential of a cell at standard conditions. So what are the some of the things? What are the conditions at standard? So standard conditions involve what's the temperature, what's the pressure, what's the concentration.
The concentration is 1 molar.
So 1 molar concentration. They like asking these questions. Mhm. What's the temperature?
25 degrees.
Okay. What's that if you take it to Kelvin? Is it 300 kelvins? It's like I'm forgetting these calculations.
adding 25 to 273. It's 298.
Okay, 298. Um, then temperature, oh, pressure.
One
Pressure, I think, is 1 atmosphere.
Okay, 1 atmospheric pressure. So these are the three conditions that make yeah, the standard conditions. These are the conditions. So that's the E cell that we've been calculating. So later on, we are going to learn about calculating the non-standard cell potential. Okay, so there's no the difference is, I don't know if you can call it a degree or something. That Casimbo is not there for the non-standard. Okay, so that's why we'll now begin talking about the next equation and all that. We'll look at the Q and the K. Yes, Gibbs free energy is something that is next that we are to talk about. And then we'll look at electrolysis, we'll look at different batteries. Hopefully by tomorrow morning, actually, I'm posting videos about all this. So tomorrow there will be a video about the next equation, the Gibbs free energy, and everything that we've talked about so far. And the calculations of Q and K under standard and non-standard conditions. So for tonight we'll end here. So we'll have the class again on Saturday where we'll review the other part that we've not talked about. But hopefully within the week, make sure you access the introduction videos and the next equation and everything else. Unless there is any other question, we can actually get to end here. Any question?
Is the salt bridge always going to be made up of sodium sulfate? Or how do you know?
No. So just as the name entails, salt bridge. So there are a lot of salts. Okay. So for now, don't worry yourself about how do you choose. Okay. You understand later on. So by the way, I just need to point out to say, for example, the example that we are from having, right? It's not always that you're supposed to have the same sort bridge. So for example, if I ask you a question to say what sort bridge would be useful, so you may find that the examiner will have even up to 4 different sorts. Okay, so don't be like, which one? So just think about it. Look at the ions. Think about which one can react better, and all that. Okay, so we can end here. If you want to register, you can inbox any of the people who've been posting in the group so that you access the videos tomorrow morning. Good night.